Today we are looking at chemical engineering thermodynamics. So we start with an introductory part of it, which are some basic concepts, and then we'll move to parts of lecture two. That's what we do for today. Thank you. So we're going to look at explaining some of the basic concepts like I mentioned. Then we'll look at some basic variables as well and how they are measured. So when we talk about thermodynamics, we are looking at the scientific study of energy, and it's a branch of both physics and engineering science. When it comes to the science, they are normally just interested in getting understanding of the physical and chemical behavior of these quantities. But for engineers, we want to study these systems and how they are going to interact. So we are not just looking at understanding the behavior, but then how we can also use it to do things in society. So we are going to apply principles from thermodynamics. And, and we are come to learn about principles from thermodynamics. And we combine these principles with things we learn from other courses as well, so that we can use them as engineers to solve societal issues. Okay. So for every discipline, there are terms that we have to be familiar with, right? So we would need to understand the vocabulary that's associated with thermodynamics. So we'll look at some basic definitions. And one of those definitions is what we call a system. So a system is what we are looking at, what we are studying, what we are observing, right? So we say that it can define it as a region in space that is chosen for scientific study. So it's basically something that we are focusing on to study. Okay. Now, when we talk about systems, we can have an open system, we can have a closed system, we can have an isolated system. And I know that you came across this when you were doing physical chemistry. So I want someone to help us out. What is an open system? Please, can you hear me? Please, can you hear me? Said it's slow. Mm, let me try this. Please, is it clear? Is it clear? Can you all hear me? Hello. Okay, sure. So I was saying that we can have different kinds of systems, and a system is that which we are considering for study. So I was saying that I know we've done this in physical chemistry. I want someone to help us out. What is an open system? Anyone? What's an open system? Okay, so Anthony Victoria says it can exchange mass and energy, usually in the form of heat with its surroundings. Okay, so that's very true. So an open system is one that can exchange mass and energy with its surroundings. And how about a closed system? Anyone? We did this in physical chemistry, so let's not spend too much time here. Anyone? Okay, so we have two good answers here. So we can exchange energy, but then not mass. Okay, so that's very good. And then for an isolated system, there's not going to be any transfer, right? So for open system, we have mass and energy that can be transferred across the boundary. For a closed system, we can only have energy being transferred across the boundary. But when we have an isolated system, there's no exchange at all. That's very good. Okay. Now we need to be able to define the boundary for a system. So when we talk about the boundary, we are talking about that part that differentiates the system from the surroundings. And we can have different kinds of boundaries. So we can have a fixed boundary or a moving boundary. So we can see from the picture up here, this is in a particular cylinder. So the edge of the cylinder serves as a fixed boundary. It's not going to move. But then this part here is a piston. It can move up and down, but it's also serving as a boundary between the system and then the environment. So that is a moving boundary. You can also have real and then imaginary boundaries. So a real boundary will be something that is a bit tangible. But for an imaginary boundary, it may not be something that we can see, but we are defining that region as a space between the system we are studying and then the environment. I hope it makes sense. Okay, someone says I should take it again. Okay, so I'm coming. Okay, so what I'm saying is that we can have different kinds of boundaries. So a boundary is just that part that separates the system from the surroundings. So if we look at this over here, we have a cylinder, right? The ends of the cylinder serve as a fixed boundary. They are not moving. But then we have this part as well. It's a piston. It can move up and down. So as it moves, it would still be forming a boundary between the system and then the surrounding. So it's a moving boundary, right? And I'm saying that we can also have real and then imaginary boundaries as well. So for the real boundary, it's tangible. It's something tangible that is separating the system from the surrounding. But for an imaginary boundary, it may not physically be there, but we are defining that region as a space between the environment and then the system we are working with. I hope it makes sense. Okay. So we've already spoken about this. We said an open system is one which would exchange both matter and energy with its surroundings. And we call an open system a control volume. Or we can also call, no, sorry, yeah, we call it a control volume. When we are dealing with closed systems, we can call them control mass because it's only energy that we are allowing to move across the boundary of the system. And for an isolated system, there is no exchange at all, right? So for an open system, it's a control volume because we are looking at a fixed volume of material. So we are looking at a fixed volume for the system. So we are keeping the volume of the system fixed, and we are looking at the movement of material and heat in and out of the system. But for a closed system, there's no material transfer. So we are keeping that material fixed. So that's why it's a controlled mass. I hope it makes sense. Please, are we all here? Okay, so someone says not really. So let's look at this, for example, right? This is a closed system. We are not allowing material in or out of it. So the amount of gas here, the fixed mass of gas here is not going to change, but we can allow heat in or out of it. So because we are keeping the mass fixed, it's going to be a controlled mass. We are not having mass moving in and out of it, right? So that's for a closed system. But when I have an open system, realize that I can have fuel coming in and I can have exhaust gas coming out. And I can also have some kind of work being done on the system, some amount of heat being transferred in and out of the system. In this case, what is being kept constant is the boundary. So the volume is being kept constant there. Not the volume of the material, but then the volume of the system, the boundary is not changing. So that becomes a control volume. So I can have material and energy
moving into that fixed volume of space. I hope it makes sense. Okay, I'll take the volume part again. Okay, sure. So what I'm saying is that if we look at figure 1B, you can see the broken lines around here. That's defining our system. That volume is not going to change, but material and energy can move in and out of that volume, in and out of that region of space. That's why we call it a control volume. Does it make sense? So we are keeping that volume fixed, and we are just transferring material and energy in and out of that system, right? But then when it comes to a closed system, we are keeping the mass fixed. So the amount of gas here is not going to change. Unlike in this case where I can have some fuel coming in and some exhaust gas coming out, there's material transfer. Here, there's no material transfer. So it's a control mass. I'm keeping the mass fixed. Here, I'm just going to keep the boundary fixed. So that volume of space is not going to change. I hope it makes sense. Someone was asking that, do you need CPC to understand thermo? There's a point where all the courses are related to each other. So you need some things at a point. Okay. Kim, you said there's something you don't understand. Which parts would you want me to go over? Kim, is it the control volume part? Okay. So let's assume you have a cup, right? You can pour some amount of water in it. You can pour some amount of water out of it. It's an open system. But then the volume of the cup is fixed. So that's what you are looking at for your study. So that cup becomes your control volume. You're not going to change the volume of the cup. You're just keeping that volume constant. And you're looking at what is happening as you're putting water in the cup and removing water from the cup. So that becomes your control volume. It's a volume of space that you are considering for your observations. Does it make sense? So someone is asking, does it mean the open system has a fixed boundary? Yes, it will have a fixed boundary. But can I be heard? Some are saying the microphone is a bit slow. Okay, just one person who says she can't hear me. Okay, okay, I'm coming. Please, is it better? Okay, I think we can continue. Okay, so now we know what a system is. We are saying that it's a region of space that we are observing, and every system would have some properties. So any characteristic of this system is what we'll call a property. And some of the very common ones we know: pressure, temperature, volume, and mass. When we talk about properties, we can look at intensive properties or we can look at extensive properties. So when we say an intensive property, it is one that does not depend on the mass of the system. Something like temperature, pressure, and density. If I should increase the mass of the system, I'm not going to change the density, right? But then for extensive properties, things like volume and momentum, if I should increase the mass of the system, I'll end up increasing those properties. So they are dependent on the mass or the amount or the size of the system. So when we are looking at intensive properties, we usually denote them with lowercase letters. And then for extensive properties, we are going to denote them with uppercase letters, with a few exceptions. So for the extensive properties, if it's mass, we can still use a small m. But then for the intensive properties, if it's pressure and temperature, we can still use capital P and capital T. Okay. Are we okay with this part? Oh, sorry. Okay. So someone is asking that, what about a closed system? Does it also have a fixed boundary? So the thing about the boundary is that it depends on what you are studying, right? You can have a fixed boundary or you can have a moving boundary in either case, but it depends on the kind of system that you are working with. Okay. So what we're seeing over here was that we can have intensive or extensive properties. Intensive properties are dependent on the mass of the system or the size of the system or the amount of what is in the system. So they are not dependent. That's intensive. But then if it is extensive, then it depends on the mass, the size, the extent of the system. So I can have a cup of water. It's going to have a particular density. And I can have a bucket of water. It's going to have the same density. But then if I should compare their volumes, they are not the same. So density in this case is intensive. It doesn't depend on how much of the material is there. But something like volume depends on how much of the material is there. I hope it makes sense. Okay. Now we can also have what we call specific properties. So they are intensive in a way. The way we come about specific properties is that we take an extensive property and then we divide it by the mass or the amount of what is in the system. When we do this, then we have what we call a specific property. So remember we said volume was extensive. If I should divide the volume by the mass, I'll get what is called specific volume. And now it becomes an intensive property. Because it is now divided by mass, if I should increase the mass, it's going to be the same value throughout. The same thing happens with energy. So if I should take the total energy in a system and then divide it by the mass of the system, it becomes the specific energy. So everything that is specific is intensive. And I can get a specific property by taking an extensive property and then dividing it by the mass, sometimes even by the number of moles of what is in the system. So yes, it's not just mass. Sometimes we can work with moles as well. And momentum, no, we can't divide by momentum. Momentum is dealing more with forces, but we are looking at amount. It has to be divided by a certain amount. So we can divide by mass or moles. Is that okay? Okay, I say says she's confused. Which part do you want me to go over? Okay, let me use this analogy again. The specific properties. Okay, sure. So this is what we are seeing. Remember the example with the cup of water and then the bucket of water. What we are seeing is that if I should take the volume of the cup of water, it's going to be different from the volume of the bucket of water, right? Because there's more water in the bucket. Now, if I should take the volume in the cup and divide it by the mass of water in the cup, what we are saying is that it's not going to be dependent anymore on the mass, on the amount anymore. So I can take the same volume in the bucket and divide it by the mass in the bucket, and I'll be getting the same value. So I can take the volume. So maybe I have about maybe 200 ml in the cup, and I divide it by the mass, because realize that the mass is going to be small in that case, and I get maybe 50 ml per gram or something. If I should do the same thing with a bucket of water, taking the volume and dividing by the mass, I'll end up getting the same value. So the thing about specific properties is that we can take an extensive property. When we divide it by mass or moles, we will get something that is intensive in nature. So it's no longer dependent on the amount of material. Okay. Now we can also look at the state of a system. So when we measure the properties of a system, right, what we are doing is we are using those things to define what we call the state of a system. So a state is basically the system under certain conditions or having certain properties. If one of the properties change, then the state would also change. So one thing to notice is that when we talk about the state of a system, it's not the same or entirely the same as the state of matter. Okay, and I'll explain it a bit further. So we are familiar with the state of matter, solid, liquid, and gas. But what we mean by the state of a system is I can have water at 25 degrees Celsius and then maybe 1 atm, and I can increase the temperature from 25 to 30. It's still going to be water. They are in the same phase, the same state of matter. But when I'm looking at states based on the definition we are working with here, they are not in the same state because now they are having different properties. One is at 25 degrees Celsius, one is at 30 degrees Celsius. And there'll be differences in some of the other properties as well, just because we've changed the temperature. So when we talk about the state of a system, we are just talking about the system under certain defined conditions or with certain properties. And if we should change one of the properties, then we change the state of the system. Please, I hope we are all there. Don't worry, when we are done, we'll send you the slides so you have all the materials. But I hope we understand this. Okay. So when we have a system that is in equilibrium, then what we are seeing is that there's not going to be any exchange of mass or energy. There are no forces that are unbalanced within the system that will cause there to be movement of material or energy. So then we see the system is in equilibrium, right? And we have different kinds of equilibrium. So we have thermal equilibrium, which means that there's not going to be heat being transferred within the system. We have mechanical equilibrium. So we have that one is dealing more with pressure. So there's a uniform pressure in the system. There's no change in the pressure, right? And we can have chemical equilibrium based on the chemical composition of the system. And we can have phase equilibrium. That's whatever phase there is, there's not going to be a significant change. I hope we get it. Okay. So that's it for the states of a system and then for equilibrium as well. Okay. Now, one thing about the state of the system is that we don't necessarily need to know all the properties of the system to be able to define the system. Sometimes you can just define two properties and then it would imply all the other properties, right? So we can't necessarily fix every property, but then we can determine maybe two properties and then be able to use that to determine the other properties. So I know you guys are familiar with the steam table because you use it in physical chemistry. So remember that you can look at a particular temperature and a particular pressure. And from there, you can decide maybe the enthalpy of the system or the specific volume of the system, right? So that's what we are just trying to say here. You can work with two properties and then find the other properties you're looking for. You don't need to fix all those other properties. You can find them just by knowing two properties. Okay. Now let's look at process and then cycle. When we talk about a process, we're talking about the change that the system is going to undergo. So the system is going to pass through different states and then gets to a final state. All these different states, when we put them together, it forms what we call the path of the process. Okay, some people said I should explain something. the phase equilibrium. Sure. Dr. Wahid, you said I should explain mechanical. Please, can you type out the question again? I don't really get the question. But then for assay, when we are talking about the phase equilibrium, what we are saying is that if I have maybe um, some amount of water and some amount of vapor, and they are in equilibrium, then what I'm saying is that it's going to be as it is. I'm not going to have more of it becoming vapor or more of it becoming water. It's fixed now. So there's no further change in it, right? Or maybe I have maybe just water. If it's in equilibrium, then I'm not going to have it changing into something else. So when we say something is in equilibrium, basically it's more like there's not going to be so much of a change. Okay, Doctor, why you said I should explain mechanical equilibrium. So what I'm saying by that is usually it deals with pressure. And maybe you have a vessel and there's some amount of pressure in the vessel. The pressure is uniform throughout. So let's say um, I have a vessel this way, and then there's pressure being exerted on the walls of the vessel, right? But what we are saying is that because it's in equilibrium, the pressure being exerted at this point, the pressure being exerted at that point, they are all going to be uniform. If I had a case where the pressure here was higher than the pressure here, then there's no equilibrium because now there's some form of imbalance. So there'll be a movement. So when we're talking about mechanical equilibrium, all we are seeing is that the pressure is balanced. Usually it's for pressure or any other mechanical thing we can consider, but usually it's pressure. I hope that's fine. Okay. Please, are we here? Okay. Daniela said she's not fine. Please, which parts would you want us to go over? The equilibrium part. Okay. Is it all of it or a particular part? The pressure part. Okay. So now let's look at this. Realize over here that we said that this indicates the lack of driving or unbalanced forces within the system. Now let's imagine something. Let's say this is our system, right? And then I have a gas within this system. Now let's say that the pressure at this point is higher than the pressure at this point. Realize that there's going to be a gradient. So there's going to be a movement in this direction of material so that the pressure becomes balanced. So in this case, the system is not in equilibrium. But if I have a case where the pressure was uniform throughout, then there's not going to be any movement of material to ensure that the pressure is balanced because now it's already balanced. So that's what we are talking about when we are looking at the mechanical equilibrium or when we are looking at the pressure. Is that okay? So there's not going to be any movement, any change. The system is basically as it is. I hope that makes sense.
Hello, Kojo.
Yes, Doc.
So if I'm to ask something, guys, what's the definition of force? Right, a force is it a push or a pull? And they usually lead to changes. Is that right? It's a push or pull that can cause a moving body to stop, a body which is at rest to move. So Newton kind of said in his first law that anytime you see that a system is stable, that's what I mean by a system is at rest. It means that the net force is kind of zero. So that when Newton was thinking about it, he was thinking about just physical forces, right? The one that we might call a mechanical force, like physical thing that can push or pull, like pressure. So usually, guys, can you hear me? Hello, am I audible?
Yes, Doc, you're audible.
Okay, I don't think so.
Yes, Doc, please, you're audible.
Hello, guys, can you hear me?
Yes, please.
So when it comes to thermodynamics, there are other kind of forces. So that's what we call a driving force. If you think of it very well, we shouldn't add driving to it. The fact that it is a force that it will drive something. Because that's the definition of a force, anything that drives, that can move things. Right? So temperature is that kind of force. It measures some form of energy. So when there's a temperature difference between two places, you see that more of that energy moves from the higher point to the lower point, and that's what force always does. It moves from a higher point to a lower point. So when molecules move from that higher temperature to lower temperature, we call that heat. So one of the main things that pressure causes, we call that flow. So usually, I hope all of you know that rivers flow from a higher point to a lower point, right? So usually, high pressure causes flow, or let's say high energy. So as Kojo was saying, if the pressures are balanced, especially if they are on the same elevation, so three things can cause flow: high potential energy, high kinetic energy, and also high pressure. You know of the two from high school. You know that when something has a high kinetic energy to move, so it stops. That's a low kinetic energy. When something is at a higher point, higher potential energy. So the last one will be pressure, which is also a form of force or energy. Now when things are on the same elevation, and if the pressure is higher at one point, that thing will flow. So if the pressures are balanced, if the pressures are balanced on all sides, it means that there will not be any flow or there will not be any kind of movement when things are on the same elevation. And we say those things are in mechanical equilibrium. I think you should continue.
Okay, thank you, Doc. So we'll continue with the process and then the cycle. So what we're saying was that when we have a system at a particular state, it can undergo certain changes and then end up at a new state. So those changes it goes through are what we call the process. And there are several paths that it can take. So maybe I have, once again, water at 25 degrees Celsius and then 1 atm. But then I want it to get to 100 degrees Celsius and then that's 1 atm. So what's going to happen is that I'll be increasing the temperature gradually. As I increase the temperature, every new temperature is a new state. And when I put all of these states together, they form what we call the path of the process. So the path now is the water was at 25 degrees Celsius. I heated it gradually and now I'm at 100 degrees Celsius. When we talk about a cycle, we realize that we are looking at the system at a particular state. It goes through a process and then it comes back to that same state. When it happens that way, then we have what we call a cycle. So for a cycle, the initial state and then the final state are the same. Is that okay? Please, are we okay? Okay. So when we want to describe a process, we need to define the initial state and then the final state of the process. And we can talk about the path that it would follow to get there. Right. When a process proceeds in a manner that the system remains infinitesimally close to an equilibrium state at all times, then we call it quasi-static or quasi-equilibrium. What we are trying to say is that remember we said for a process, it's going to be a change that the system is going to undergo. What we are saying is that that process is going to proceed maybe so slow that we're not really going to see a significant shift from equilibrium. But then that equilibrium will be changing gradually. When it happens that way, what we have is what we have is called a quasi-equilibrium situation. So maybe I have a particular gas, I've compressed it, and then I start to reduce the pressure just bit by bit, very slowly. So what I do is that as I reduce the pressure, the system gets to a new equilibrium state, but then it's almost not easy to detect. And I keep reducing it gradually, gradually, very slowly until I get to the new point I'm looking for. So that's what we call quasi-equilibrium. I hope that's okay. Okay, someone is asking that can we say a process is linear? Um, I'm trying to understand what you mean by linear, but then not necessarily because a process can follow any particular path. So it may not necessarily be I just go straight from here to here. Sometimes you can go through so many different kinds of pathways. Someone is asking about the quasi-equilibrium. Yeah, so what we are saying is that remember we said the process is a change, but if the change is happening in a way that the system is always at equilibrium, then we are having a quasi system. So we are just maybe changing the conditions very slowly, very gradually, by very, very small amounts. When it happens that way, what we have is a quasi equilibrium system. Is that okay? Okay. And then there are some other things we need to know. So when we see the prefix ISO, it's just talking about something that is being kept constant. So I know we are familiar with these terms: isothermal, isobaric, isochoric, or isometric. So okay, someone is asking about the quasi equilibrium that can the change be visible? And usually it's very difficult to detect as it's happening. So if it's the kind of change that you can see visually, it will happen so slowly. Daniela, please, is that fine? Okay. So as we're seeing, when we see ISO coming before a word, it's just denoting that there's something that is being kept constant. So we know isothermal processes, temperature is kept constant. Isobaric processes, pressure is kept constant. When we have isochoric or isometric, then it is volume that we are keeping constant. Then, as we said, a system is said to have undergone a cycle if it returns to its initial state at the end of the process. So we said for a cycle, the initial state and the final state are the same. Is that okay? Okay. So we can also have a system or we can have a process that is steady, and we can have one that is transient. When we say a system is steady, all we are saying is that the properties at a particular point are not changing with time, right? So I think we saw this from CPC. So the one who was asking whether there's a relation between CPC and thermodynamics, this is one of the things you can consider. So when we say it's steady, we are saying that the properties do not change at a particular location with time, but then the properties can change over the entire system. So this is what we are trying to say. If let's say I have a pipe and then maybe the temperature here is 20 degrees Celsius. Sorry for the writing. And maybe the temperature here is 30. And then the temperature somewhere here is 25. For a steady process, what we are seeing is that every time I look at this point here, it's always going to be 25. So maybe whatever is passing through the pipe is being heated from 20 to 30. But every time I check this particular location, it's going to be 25 degrees Celsius. So that's going to be a steady system. But in the case where maybe I'm in, or maybe the material is flowing through, I check this side the first time, it's at maybe 21. I check it again, it's at 22. I check it again, it's at 23. You realize that it is gradually moving towards one particular value. So it's not yet steady, it is transient. I hope that's fine. So when there's no change in the property at a particular location with respect to time, then we have a steady process, right? But then over the entire system, that particular property can change. So we started with 20, we ended with 30. There was definitely an increase in temperature, but at every location, the temperature was kept constant. So that's a steady process. I hope that's fine. I hope that's okay. Okay. Now let's look at temperature. Okay, someone says I should come again with a steady state and then a transient. Okay, so this is what I'm saying. I might have a pipe, right? And then what is coming into the pipe is coming at maybe 20 degrees Celsius. What is coming out is coming at maybe 30. Somewhere in the middle, it got to 25. At another point, it got to 27. What we are saying for a steady process is that if I check the temperature here at any point in time, and it is always fixed, it is always at 25, it's not changing, then I have a steady process. But a steady doesn't mean that it's the same value throughout the whole system. Because remember, we started at 20, we ended at 30. So we know that it's being heated across the pipe. But at a particular location, that temperature is always going to be 25. If it was a transient process, realize that it is now trying to get to that steady state. So the material is flowing in at 20. It will first get to 21, get to 22, get to 23, get to 24, get to 25, and then stay at 25 at that particular location. So now that's a transient process because now the temperature at every location is not constant. But if the temperature at every location is constant, then we have a steady process. Um, Steady does not necessarily, well, it depends. In a case like this, we can say that it's a steady state, but then we can't say that's equilibrium because there's a temperature difference. This side is at 20, that side is at 30. So there's definitely going to be some kind of heat transfer that is coming into the system. You get it? So we can't say that this is in equilibrium yet. That's for the entire system. Okay. Let me see if we can use another example. Okay, let's say you are measuring the pH, right, of a material in the lab with a pH meter. Okay, you realize that when you put the pH meter into the system and maybe you've added your base to it, you see that the values on the meter will be changing for a while before it gets to a point where now it is constant. It doesn't change anymore. That process where it is taking time to change, where you see different values, is the transient point. But the point where now the concentration isn't changing, it is fixed, that becomes the steady point. I hope that example is more understandable. Let's see. Okay, that's fine. Okay. So now let's talk about temperature. When we talk about temperature, we're talking about the measure of how hot or cold a body is. And we are all familiar with the kinetic theory of matter from SHS, right? So what we are seeing here is that the earliest precise measure of temperature was the volume occupied by a known amount of gas at a known low pressure, right? So we know that even if we use maybe ideal gas equation, PV is equal to RT, we can make T the subject, and we know that is going to be dependent on some pressure and some volume. So that's how they determine temperature, the earliest determination of temperature. And if we should look at the units, it's going to end up something like this. So these are going to be the units. It's going to be a pressure term, a volume term, and then a mole term. Especially if we use the ideal gas equation that we know. right? And then we can also now or they now also determine that the units for the temperature, we can now just keep it as Kelvin or maybe degrees Celsius, where we now introduce the universal gas constant into it, right? So temperature is now going to be treated as a fundamental quantity. Is that okay? Someone is asking why. Please, why for what exactly? Why is it being treated as a fundamental quantity? So you realize that the fundamental quantities are such that um, they are not obtained from other quantities, right? So in this case, what we are saying is that it is the temperature that we can use to determine what's happening with the pressure and then with the volume as well. Just like mass is a fundamental quantity, um, time is a fundamental quantity. We can combine these to get other things, but we don't derive them by combining other things. I hope that makes sense. So they treat it as a fundamental quantity because you can't just maybe take um, length from somewhere, time from somewhere, then merge them to get temperature. Is that okay? Okay. So when it comes to measuring temperature, it's done based on the concept of thermal equilibrium. So remember we said for thermal equilibrium, we are not going to see any change, right? And the zeroth law of thermodynamics and then other things would help us be able to determine temperature in a way that is predictable, in a way that we can repeat. So if we are having two different bodies at different temperatures and we bring them into contact with each other, we know that what's going to happen is that there's going to be a transfer of energy from the one at a higher temperature to the one at a lower temperature. So the one that's at a higher temperature is going to have a reduction in its energy. And the one that's at a lower temperature is going to gain more energy, right? And if we keep them in contact for long enough, then they are going to attain the same temperature. At that point, we say that they are in thermal equilibrium. So now there's no transfer of, or there's no net transfer of energy between them, right? So maybe I have one material at 50 degrees Celsius. I have another material at maybe 20 degrees Celsius, and I bring them into contact with each other. The one at 50 will now have the temperature reducing gradually, or it will have its energy reducing gradually. The one at 20 will have its energy increasing gradually until the point where they both have the same temperature now. And when they have the same temperature, there's not going to be any further transfer of energy. So in that case, we have thermal equilibrium. In this concept is used when it comes to temperature measurements. So what happens is that when we want to measure the temperature of a body, the body that is of interest usually is much larger than the body that you are using to do the measurements. So because it is so large, it has so much energy that as it transfers its energy to the smaller one, it's not going to lose so much. So let's use the example again. Maybe I have a particular material at 50 degrees Celsius, a very huge material at 50 degrees Celsius, and I have a very small material at 20 degrees Celsius. Realize that when I put them in contact with each other, the one at 20 degrees Celsius will quickly get to the 50 degrees Celsius temperature. So now I can look at that change in temperature and determine that, okay, there was an increase in the temperature up to 50 degrees Celsius. So it means the temperature of the bigger body was at 50 degrees Celsius. I hope that makes sense. So let's say I have one material at 50 degrees Celsius here. Then I have a very small one at 20 degrees Celsius here. If I should join them together, realize that the bigger one is going to lose a lot of energy. So it's not going to lose so much energy. It's going to lose some energy. to the small one. But because it is so huge, the amount of energy it has to lose is very small. So it's not going to change the temperature significantly. But then the small one, because it is so small, even a little amount of energy will cause it to increase by a lot. Okay, so someone is asking for a real example. So let's look at an actual thermometer. If we have someone who has to go to the hospital, right, and you want to measure the temperature of the person, realize that maybe your temperature is 35 or 36 degrees Celsius, and then the thermometer might be at room temperature. And then once it comes into contact with your body, you are going to give off some kind of energy to the thermometer. And then its temperature is going to rise to meet your temperature. So you are losing some amount of energy. But because you are a bigger body and you have a larger heat capacity, you are not going to lose so much energy that your temperature will change significantly. I hope it makes sense. Okay. So that's how these things work. And when we look at the zeroth law of thermodynamics, all we are saying is that if we have two bodies that are in thermal equilibrium with a third body, then they are also in thermal equilibrium with each other. So all that is saying is that I have maybe substance A, I have substance B, and then I have substance C. If A and B are in thermal equilibrium, and then A and C are also in thermal equilibrium, then B and C are in thermal equilibrium. That's what we are just trying to say by that law. Okay. So we can also now look at temperature scales. The reason for having scales is so that it makes the temperature measurement a bit easier. So when we are looking at these things, all we are saying is that there's a point where um maybe like we are working with water, or it was actually based on water. So there's a point where water would boil and turn into vapor. There's a point where water would freeze and become solid. So different people will look at these different points and then give them a reference. So one person will say that, okay, the points where water freezes, let's keep it at 0. The points where water is going to boil, let's keep it at 100. And then they now have the Celsius scale. So there are different scales that we have, right? And we also have absolute scales as well. So you need to be able to change from one to the other. How to change from Celsius to Kelvin, how to change from Celsius to Fahrenheit, how to change from Fahrenheit to Rankine, all these things. So these are some of the conversions down here. Is that okay? I think once again, we saw this in physical chemistry. So the temperature conversion shouldn't be so much of a difficulty to us. Okay, and that's fine. So I want us to try this example. Or I think I'll do the first one. And I want you guys to try out the second one and then give me the answer. And Obed, please, you said you don't get something. The zeroth law. Oh, okay. So what we are saying by that is if I have one material, so let's say I have three materials, this and this are in thermal equilibrium, and then this and this are in thermal equilibrium, then it means that these two are also going to be in thermal equilibrium. Right. So let's see if we can make this a little bit practical. So let's say we have three different metals. Okay. There's one that is in the middle. So when I join it to the other two, realize that there's no heat being transferred across them. So it means that it's in equilibrium with the one on its right and in equilibrium with the one on its left. I think, let me see if I can draw something to make it better. So let's say I have three different pieces of metal and they were all at different temperatures. But now that I've put them together and I've waited for some time, their temperature is the same. What I'm seeing is that this metal piece in the middle, because there's no heat transfer between this metal and then the one on the right, and there's also no transfer between this metal and the one on the left, then it means it's in thermal equilibrium with both of them. And because it's in thermal equilibrium with both of them, then it means that those two are also in thermal equilibrium with each other. So if maybe the one in the middle got to 30 degrees Celsius, the one on the right will also get to 30. The one on the left will also get to 30. But then the one on the left and the right are also in equilibrium with each other because they are at 30. I hope it makes sense to you now. Okay, I think we can go on there. So I was saying that we'll try this. I'll do the first one with you, and then I'll let you guys try the second one. Then you give me your answers. Okay, someone is asking why the term zeroth law. Before I answer that, yes, Amanda. So yes, at the end they'll all be 30 degrees Celsius. The reason why it was called the zeroth law is because um when they started working out thermodynamics, they defined what we call the first law, then the second law of thermodynamics. And then they realized that this law is more fundamental than those laws, but they discovered it later on, or they defined it later on. So that's why they gave it the term zeroth. Yeah. Okay. So let's look at this over here. We are being told to calculate the temperature of a fluid when both a Fahrenheit and a Celsius thermometer are immersed in it under the following conditions. So the first condition is that the numerical reading is identical in both thermometers. So before we get there, let's look at this. We are looking at the conversion between um, Fahrenheit and Celsius, and we can see that over here. Right? So we know that the temperature in Fahrenheit is 1.8 the temperature in Celsius plus 32. Now, what we are saying is that the numerical reading is identical in both thermometers. So we are saying that the value on the Fahrenheit thermometer should be equal to the value on the Celsius thermometer. So that's what we have as our first point here. So the value on the Fahrenheit scale should be equal to the value on the Celsius scale. We want to represent it with a variable A. But we know the conversion between Fahrenheit and Celsius as this. So I'm just going to replace the Fahrenheit here with A, and then the Celsius here too with A. So I'll have A to be equal to 1.8 A plus 32. Then I can make A the subject, and I'll get minus 40 degrees. To realize that if I have minus 40 degrees Fahrenheit, and I try to change it to Celsius, I'll still get minus 40 degrees Celsius. Are we fine with that? Okay. So I want us all to try the B. The Fahrenheit reading is numerically twice that of the Celsius reading. So let's try it. You can type out your answer. Let's use the next 2 minutes to do this. Yeah, let's use the next 2 minutes to do this. So when you're done, you can just type out your answer. Okay. The B part is saying that the Fahrenheit reading is numerically twice that of the Celsius reading. So it means that whatever value we get on the Celsius scale should be equal to twice the value we get on the Celsius scale. So we can see that this T degree F should equal to 2 of T degrees Celsius. Is that okay? Okay. So we have an answer. So I should please check it. It's not minus 160. It's positive. Did anyone else get the answer? So what we said was that, okay, that's good. So what we said was that the temperature in Fahrenheit should be twice the temperature in Celsius. So that's what we have here, what you've highlighted. right? So we can represent the temperature in Celsius with the variable B. That means the temperature in Fahrenheit will be 2B. So if I should put that in the conversion and I make B the subject, I'll get 160. So realize that 160 degrees Celsius, if I should convert it to Fahrenheit, will be 320 degrees Fahrenheit. Okay, that's good. Okay. Now we can consider pressure as well. So we've looked at temperature. When we talk about pressure, we know that pressure is just the force that is acting normally on the unit area, right? And we know that when we are looking at the kinetic theory of matter, then we can consider the average kinetic energy per unit volume. I hope we know where that is coming from. Okay, someone said I should go over the calculation. So before we get to the pressure part, what we are seeing is that we wanted the temperature in Fahrenheit to be twice the temperature in Celsius, right? So if our temperature in Fahrenheit is twice the temperature in Celsius, then we can represent the temperature in Celsius with the variable B. Then it means the temperature in Fahrenheit will be 2B. We know that if we are converting from Fahrenheit to Celsius, then this is the relation we use, the one up here. So the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So I'm just going to replace the temperature in Fahrenheit here with the 2B, then the temperature in Celsius here with the B, and I'll get this expression. Then I can make B the subject. When I do that, I'll get 160. But remember, that was for the temperature of the temperature in Celsius. Okay, you're welcome. So what I was saying about the pressure is that it's the force that acts per unit area. But then we can also define it as the kinetic energy, right? That's acting per unit volume. So realize that if you look at it in terms of the dimensions or the units, we have force over area. If I should multiply force by a certain distance, I'll get energy. If I should multiply area by a certain distance again, I'll get volume. So force over area and energy over volume are going to have the same units. That's why this holds when you look at it in terms of its dimensions. Okay. Now, when we talk about the pressure, the actual pressure at a given position is called the absolute pressure. And we measure this relative to an absolute vacuum. So where we have absolute zero pressure. So if we should measure a pressure relative to a point we are considering as zero, then we call that the absolute pressure, right? But then when we look at most pressure measuring devices, we calibrate them to reach zero in the atmosphere. So we now take the atmospheric pressure to be the starting point or to be the 0 point. When we do that, then what we rather have is now called the gauge pressure. Is that okay? Interesting question. No, it's not the same as specific pressure. It's not the same as specific pressure. If it's specific, remember we are dividing by a certain mass or moles. Okay, I'll go over this part again. So what we are saying about the pressure is that we can have a case where we are measuring it relative to an absolute 0 point where there is no pressure. There is no pressure being exerted at all. So we call that absolute zero pressure or absolute vacuum. So if I should measure my pressure with that as my starting point or that as my 0 point, then that becomes what I call absolute pressure. But the thing is that we don't usually measure pressure from that 0 point where there is no pressure at all. We measure it relative to the pressure of the atmosphere around us. So when we do that, that atmospheric pressure now becomes our starting point. And so we call that gauge pressure now. Okay, someone says I'm talking too fast. Sorry. So this is what we are trying to see. There's a certain point where the pressure is considered as zero. There is no pressure there at all. There's a certain point in the atmosphere. So I'll represent that with A. So this is the pressure of the atmosphere, right? And then this is our pressure of interest. So I'll represent this with P. So what we are saying is that if I measure the pressure P by considering this 0 point, the original point, means I'm measuring the pressure difference this way. So this is going to be my 0 point. This is the pressure I'm measuring. If I measure the pressure this way,
The one we have is called absolute pressure. But sometimes it's hard to do it this way. It's easier to rather work with the pressure of the atmosphere around us. So if I should measure the pressure from this point to this point, then the pressure I'm having is what I call gauge pressure. Is that okay? So in the first case, we are considering absolute vacuum, or the point where there is no pressure at all, to be our reference or to be our starting point. Then we have what we call absolute pressure. In the second case, we are considering the atmospheric pressure to be our starting point, or to be our 0 point, or to be our reference point. In that case, we have what we call gauge pressure. Is that clearer now? Okay, that's good. So if I want to find my absolute pressure, and my absolute pressure is greater than my atmospheric pressure, right? Then I can see that the gauge pressure is the absolute minus the atmospheric. So this is what we are just trying to say. The value here, this P here, minus this A here, will give me the gauge pressure. So it's the same thing we're saying all along. Gauge pressure is just the difference in the pressure. That's going to be the absolute pressure minus the atmospheric pressure. Is that going to be fine? Or let me do it this way. I think this would be better. So for absolute pressure, we said we are measuring it from this starting point, right? And then for the atmospheric pressure, it is from this point up to this line here. That's atmospheric pressure, the pressure of the atmosphere. So if I should find the difference between them, this minus this, what is going to be left is just this top part, which is equal to what we defined as our gauge pressure earlier. Is that okay? Yes, gauge pressure is actually a difference in pressure, yes. So I say you are right. It's a difference in pressure between the absolute pressure and the atmospheric pressure. So we know atmospheric pressure is 1 atm, right? So that value was gotten from measuring from down here to this side. This side here, this part here is the 1 atm. And whatever value I get from my absolute pressure, that is taking it from the 0 point all the way to the P, becomes the absolute pressure. If I find the difference between them, it gives me what we call the gauge pressure. Please, are we okay? Okay. Now we can also have vacuum pressure as well. So in this case, the absolute pressure, is now lower than the atmospheric pressure. So what we would have instead is, instead of we having the P up here and the A down here, what we are saying is that, once again, I have my 0 point, and this time my the atmospheric pressure, the A point is now higher, and then the P point, where I had my absolute pressure, is now lower. So now if I should find a difference, right, this is going to become what we call a vacuum pressure, because now I'm going below atmospheric pressure. So it's still going to be something similar. I can take the atmospheric pressure, that's this part here, from A to the 0 point. And I can take the absolute pressure, that's from P to the 0 point. And if I find the difference, what is left is going to be this point. So that becomes the vacuum pressure. Please, are we okay? So the only thing is, or if you want to really get this, what you can do is that you can actually decide to draw the lines. So you have a 0 point, you have your A, that's for atmospheric pressure, and you have your P, that's for absolute pressure, right? So if I should take the line from 0 to P, it's always going to be absolute pressure. The line from 0 to A is going to be atmospheric pressure. If P is greater than A, and I find a difference, what is going to be left is just this part here. So that becomes gauge pressure, right? Once again, I have my 0 point, but then this time, P is lower than A. And remember, we said if I take it from 0 to A, it is atmospheric pressure. From 0 to P is absolute pressure. If I find the difference, it's going to be just this side. What is going to be left is just this side. And now because this time P is lower than A, we call it vacuum pressure. This is how okay. So the absolute pressure, we are just saying that is the measure of the pressure from absolute zero, from the point where we consider that there is no pressure at all. So an absolute vacuum, there's zero pressure. The pressure there is zero. When we measure from that point to the pressure we are looking at, that becomes absolute pressure. So someone is asking that there's no gauge here. Which part exactly? So the thing about the vacuum pressure is that it is a gauge pressure, but in this time it is lower than the atmospheric pressure. It's below the atmospheric pressure. You are finding the difference between your absolute and your atmospheric pressure, but in this time your absolute pressure is lower than your atmospheric pressure. Okay. I think we can continue from this point here. So, okay, we've already spoken about this. I think this is a repetition, how we measure temperature. So that's it for the first lecture. But before I move on to the next, are there any questions? We would start with the initial part of lecture 2. But are there any questions? Yes, please. So we use gauge when the absolute pressure is higher than the atmospheric, yes. Please, are there any questions? Someone is asking when the recordings will be sent. So once again, they are being edited. We'll make them available to you. We'll make them available to you. At least you should get the CPC ones this week. Okay. Let's move to the second lecture. We'll just take some parts of it for today. Okay. So now I want to look at still the properties of material, but then this time we are considering pure substances, right? And then we want to look at things like phase change, and then we'll look at a few diagrams. So we'll just start with an introductory part to this. But before we go on, when we say something is pure, what do we mean by pure? Anyone? When we say something is pure, what do we mean by pure? So it says it contains only one kind of a substance. Okay, that's very true. And then Nana Kwame says it has uniform composition. Okay, so that's it. So when we say something is pure, it has a uniform composition, or yes, it contains one kind of a substance. And I like that answer because he said one kind of a substance. Another person says that it means there are no impurities. Okay. So when you're talking about a pure substance, as you've all said, right, it's something that is having just one particular material or groups of materials. So we can have a mixture, but then it is a pure mixture, right? So I can have maybe just water in its pure state. There's nothing else in the water, right? Or I can have a mixture of maybe water and alcohol, but then that mixture is pure because it's homogeneous. But in a case where I have something like oil and water, I can't say that it's a pure system because they are not going to mix together. So it's not going to be a homogeneous system. Is that okay? So we can have things that are pure that might have a number of materials together. So we can see the last points down here that a two-phase system can also be classified as a pure substance if both phases have a uniform composition. Please, is that fine? Please, is that fine? Okay. Yes, Obed, you're right. So yes, it's heterogeneous, the oil part. It's not homogeneous. Okay, so let's go on. Now we can look at the phases of substances. So there are three major phases. We can have solid, liquid, and gas. Please emphasis on the major because we'll come back to that. Okay. When we talk about the phase, we are looking at there being differences in maybe their molecular arrangement, how the molecules are arranged, the strength between the intermolecular forces or the strength of the intermolecular forces, and then how much energy the individual molecules have, and then their specific volume. So if we should look at it in terms of the strength of intermolecular forces, know that the forces between the molecules of solids are stronger. That's the forces of attraction. They are stronger than that of liquids, and they are stronger than that of gases when we consider the forces of attraction. When we consider the energy levels, you know that gas molecules have more energy than liquid molecules, which have more energy than solid molecules. Then when we consider the volume, the specific volume, you know that gases will occupy a larger volume as compared to liquids and as compared to solids for the same mass of material. Please, does that make sense? Someone is asking even solids. For which parts? Is it the forces, the molecule, the energy level, or the specific volume? Okay. She says she understands. So then that's fine. Okay. So the thing about the phases is that temperature and pressure can affect the phase of a material. So if we should increase temperature, that's heating, right? We can cause it to be a phase change. Or if we should do compression, so we are increasing pressure, we can bring the molecules closer together. So that can also lead to a change in phase, right? And we are seeing that although there are differences in the exact temperatures and pressures at which these changes occur, most pure substances exhibit the same behavior with changes in temperature and pressure. So what we are saying is that, yes, it's true that for one material, the phase will change at a different temperature and pressure than another material. But then the way they all work is the same. So maybe I have water at 1 atm is going to boil at 100 degrees Celsius and then become a vapor. I have alcohol at, I think, 78 degrees Celsius and 1 atm. It would also boil and become vapor. So they become vapor at different temperatures. But I realize that they are following the same kind of behavior. They start out as liquid, they start to vaporize. So you have a mixture of liquid and vapor, and then they all become vapor at the end of the day. So they have different temperatures and pressures at which their phases will change, but they exhibit the same kind of behavior. Is that okay? Okay. So now we are going to consider what we call PTV changes. So this is just representing pressure, temperature, and volume changes in most pure substances. So how they behave. So the thing about pure substances, especially when you are starting from liquids, is that I can have a certain amount of material here, and it's a liquid. Let me bring this down a bit. So this is temperature against specific volume. So the liquid has a particular volume. Then I increase the temperature gradually. I increase it gradually, I increase it gradually. The volume will increase slightly because I'm increasing temperature, I'm adding more energy. So the molecules become more energetic and then they move away from each other. So the volume will increase slightly. And it gets to a point where now I'll keep the temperature constant and it will now start changing to vapor. So remember from physics, sensible heat, latent heat, right? We get to a point where now we don't need to continue to increase the temperature. We keep the temperature constant and it now starts becoming vapor. So it gets to point 4, where now all the liquid has turned into vapor. Now I can increase the temperature again and then cause the volume to increase even further. You realize that as it is changing from liquid to vapor, the volume is increasing. So we can see that here at point 2, the volume is lower than at point 4, right? Because liquids have smaller specific volumes as compared to gases. And this is how most pure substances are going to be, especially when you're starting from a liquid point. So they'll be liquid. You increase the temperature, the volume would increase slightly. Then it gets to a point where you keep the temperature constant and it now starts changing to vapor. As it changes to vapor, the volume would increase a lot. Then everything becomes vapor. You can now increase the temperature again and then cause the volume to increase further. Are we all fine? So what we are saying is that when heat is added to a fixed mass of water at constant pressure, the temperature would increase with the added heat, and then the specific volume would also increase. Then when it starts to boil, the temperature remains the same. Because remember, we said latent heat. When there's a phase change, the temperature, the pressure are kept constant, right? So that region is called the saturated region. It's saturated because we have a mixture of liquid and vapor, right? Then that temperature will remain constant until all the liquid becomes vapor. Now, if we increase the temperature further, we are now going to have it becoming, it's already vapor, so it now starts to expand a little bit more. So now we need to be familiar with the different regions we have. So here, from point 1 to point 2, we have what we call a compressed liquid, right? Because it's in a liquid form. When it gets to point 2, it becomes a saturated liquid. So saturated liquid means that it is a liquid, but then it is at the verge of changing into a vapor. Then from point 2 to point 4 is a saturated mixture. So we have a mixture of liquid and vapor in there. When it gets to point 4, okay, there's a question. I'll address it soon. When we get to point 4, it becomes saturated vapor. Saturated vapor is that everything is a vapor, but then it can easily be sent back to become a liquid. Then from point 4 upward, we are going to heat it even further, so it becomes a superheated vapor. So someone is asking that at point A, the volume increased, but the indicated on the upper part of the line, compressed. Yes, it's starting from a compressed point, but then as we increase the temperature, it will start to expand. So the liquid at that point was a compressed liquid, and then we now started to increase the temperature for it to expand. Is that okay? Okay. So please take note of how this diagram is, right? You realize that it is, if you look at the individual lines here, they almost look similar. So what they did was that they considered, or before I go into that, remember we have here temperature against volume. And if you look at the head, we're looking at it at constant pressure. So this is at 1 atm. When we change the pressure, the curve will change slightly. So these are the same kinds of curves, but then at different pressures. So you can see at these points here, we have the pressures labeled there. So there are different pressures that they are all working at. And what we are doing is that we are just observing what happens as we increase the pressure. So what we are saying is that there's a point where when we increase the pressure so much, the difference between the saturated liquid and saturated vapor becomes hard to see. I'm coming. So someone says at point A, the volume, is it compressed at point 2? So at point 2, no, it's not compressed. At point 2, it's saturated. It's not compressed, it's saturated. Okay, so this is what we are saying. If I look at the curve where the pressure was 0.01 megapascal, so realize that I would increase the temperature to a certain point. I keep it constant and now start shading into vapor. But when I increase the pressure to 0.1 megapascal, I need to increase the temperature even more. The reason is that if I'm increasing the pressure and I'm increasing the temperature at the same time, what is happening is that the temperature increase is trying to cause the material to expand. But then that increased pressure is going to try to push the material back together again. So I'll need more heat. That requires a higher temperature before I can now start changing it to a vapor. And what happens when we make the pressure very, very high is that we need so much temperature to cause it to expand. But then the pressure being so high is also pushing the molecules together again. So now the system is trying to change from liquid to vapor, but then that pressure is also pushing it to stay as a liquid. So the difference in the space from where it changes from liquid to vapor gradually reduces. Because over here, I will have the pressure pushing against it. At this point up here, the pressure is pushing against the material. So it is trying to keep it as a liquid. But then the temperature is also trying to cause it to expand into a vapor. So that saturated region is very small. So it is like this kind of battle between the temperature and the pressure. When it gets to a point where now the temperature just goes high enough and then it just changes it into a vapor, right? So as we increase the pressure, what we are saying is that as we increase the pressure, the saturation region reduces. So you will start out as a saturated liquid, but then it wouldn't have a significant change in the volume before it becomes a saturated vapor. right? Oh, someone is lost. Okay, let me try and explain this again. So let me start from this point here. So what we are saying is that we have a liquid, we heat it to a certain point, it becomes saturated. When it's saturated, we are saying that it is liquid, but then it can now start becoming vapor. So on this line, it's a mixture of liquid and vapor. When it gets to point 4, it is a vapor, right? Now from point 2 to point 4, it's changing from liquid to vapor, so the volume is increasing. Okay, yes, I'll use this to explain the second part. So we are moving from liquid to vapor, so the volume is increasing. What we are saying is that when we are having the pressure to be very high, we won't see a significant increase in that volume because while we are trying to increase the temperature to cause that volume to expand, the pressure is also pushing against it. So you realize that that saturation region reduces. So you need a very high temperature for it to even become saturated. And when it becomes saturated, because the pressure is high, you can't have the volume expanding. So the specific volume is very small. So that saturation region is very small until it gets to a point where now it changes fully to a vapor before it can continue expanding again. Does it make sense? So the straight line here, the one that is horizontal, is representing the saturation point where we are having the liquid changing to vapor. You know that when the liquid changes to vapor, the volume is supposed to increase. So at a low pressure, we see that that line is very long. It's a wider space because the pressure is very low. So it's not going to push against the molecules to reduce the volume. But when the pressure gets very high, realize that that space becomes smaller. So the pressure is pushing against the molecules. So the volume is not going to expand as much as you might expect it to expand. And someone said he didn't get that. So this is what we are saying. This region here, this straight part here, is representing the saturation region. So the liquid is changing to vapor. When the liquid changes to vapor, we expect the volume to increase, right? Because vapors have larger volumes than liquids. But then the issue is that if I should increase the pressure, while that vapor is trying to form and expand, the pressure is pushing against it. So the pressure pushing against it is going to cause the volume to rather having, instead of me having a very high volume, or rather be having a small. So the volume is not going to change significantly, especially as we increase the pressure more and more. So if you look at this point here where we have 50 megapascal, realize that the change in the specific volume. So if I take this point and this point, the specific volume, it's a very small change as compared to when the pressure was very low. Because the high pressure is going to push against the molecules and it's going to prevent the volume from expanding. Yes, the pressure is preventing the volume from expanding as the pressure increases, exactly. And because it is preventing it, it means I need more energy for it to become a vapor. That's why I realized that the points where they now start becoming saturated liquid are increasing. So if you look at the previous diagram, the point 2, that's the start of the straight line. If I look at it for all of them, it starts increasing because I'm pushing the molecules together. I need more temperature for it to now actually start becoming a vapor. Is that okay? So we get to a certain point where the pressure is so high that there's not a significant difference between the liquid and the vapor phase. We can't really distinguish between them. When we get to that point, we call it the critical point. So the critical point is the point where we don't really see much of a distinction between the liquid and then the vapor phase, right? So I'll send you something to help you visualize that a bit more later on. Are we okay? Okay, I think we can continue. Okay, that's fine. So let's talk a little bit more about the critical point. Now, this particular curve we are seeing here is actually, let me put it this way, it's a combination of all these curves. So this is how they went about it. If I have all these curves here and I join all the points 2 to each other, so I join this point to this point, all the parts where I have points 2, and I join all the points where I had points 4, right? All these points to each other. I'll end up with the curve on the next page. So
Oh, sorry. So I'll end up with this curve, right? So all they did was that all the points 2 and all the points 4, we are just tracing them because you're only interested in the saturated part. You don't want to consider you're not really giving focus to the liquid and then the vapor part. You're just looking at the saturated region, right? So in a minute, okay, I think we can get it. So what we are saying is that if I should join all those points to each other, it's going to give me this curve, right? Then I can pick any particular pressure and then just work with it. So the critical point is going to be that highest point up here. It's going to be that highest point that we get at the top here, right? Everything to the left of it is going to be a liquid. Realize that everything at this point here, right, that is from point 2 downwards. If you look at this diagram, from point 2 to point 1, that's all to the left is going to be liquid. Everything to the right, this side here is going to be vapor. So realize that when we look here, everything here was vapor. Everything to the right side. So if I look at each of the curves, everything to the right is going to be vapor. So everything to the right here is going to be vapor, right? And then the top here becomes a critical point. So we have our liquid region, we have our vapor region. Is that okay? Okay, someone says I should go over the critical point again. And someone is saying, I thought pressure is exerted between the walls of the container and the molecule. But are you saying the pressure among the molecules? Okay. Okay, so I think we are fine with the critical points. Um, yes, the pressure is exerted between the walls of the container and the molecules. Okay, this is what we are trying to say. If we are keeping the pressure of the system constant, so maybe let's say, for example, you are heating water, like a very practical case, right? You are heating water. There's going to be a pressure of the surrounding, right? For the water to now become vapor, it has to overcome that pressure. So that's the pressure we are referencing. If we keep that pressure constant, the pressure that is going to keep it as a liquid. Do you get it? So we are not talking about the um pressure of the molecules themselves because that pressure is going to, I think we'll get to that later on in this slide where we talk about the vapor pressure and the saturation pressure. So there's a pressure that the material itself is going to have, and there's a pressure it has to overcome from the surrounding, the atmospheric pressure. So that's what we are keeping constant. If I keep it constant, then there's a certain temperature that the system has to get to before it can become a liquid. So we are not talking about the pressure between the walls of the container and the molecule. We are talking about the pressure between the system, the material you are working with, and then the atmospheric pressure. And then there's a question about, does it mean after the critical point, the temperature is going to start decreasing for the liquid to change to vapor? Yes, after the critical point, if you want to change the liquid to vapor, no, the temperature wouldn't have to decrease. When you get to the critical point and you increase the temperature, it will now become, actually, it's difficult to distinguish. It's like a liquid vapor-like state. So I'll send you a video on that. You'd see it. It becomes difficult to distinguish between the liquid and the vapor state. But you don't have to decrease the temperature. No, you rather have to increase the temperature. If you decrease the temperature, you're going to come back to the liquid form. Is that okay? Okay, sure. So we are saying the critical point is defined as the point at which the saturated liquid and saturated vapor states are identical. So it's difficult to distinguish between saturated liquid and saturated vapor, right? At pressures above the critical pressure, we don't see a notable phase change. And at all times, there's only one phase. So if we should heat the liquid at a supercritical pressure, it will lead to something that is vapor-like, but we can't really tell when that change is going to
Hello, please, can you hear me? Sorry. So the thing about the critical point is that when the pressure becomes very high, or when we get to what we call the critical temperature and critical pressure, yes, it becomes hard to distinguish between the liquid and vapor. So it's like you have a liquid, you have a vapor in the system. You don't see the points where one becomes the other. So you can't really tell how it is at that moment. I'll actually send you a video on that and you can visualize it so that you can see it clearer, right? And you're asking that what actually happens after the critical temperature for the liquid to turn to vapor. So after the critical temperature. So if you've gone past the critical temperature, you are more in like a vapor-like state, but you can't really define how that state is. So if you want to take it to vapor, you have to make sure that it comes within certain conditions. So you have to drop it to a certain temperature and a certain pressure. Then you can have it back as a vapor. Sorry. So there's a particular pressure and temperature that you can drop it to, and you have it just as a pure vapor. Someone is asking that is it that the pressure reduces? No, we are looking at it as a particular pressure. So the critical point, we're considering it at a particular pressure and a particular temperature, right? So we can reduce one of them, and then it will affect a particular kind of thing we are going to have. So if I have it at a particular temperature and a particular pressure, and I should reduce the pressure, I'm going to have it more like a vapor. If I should increase the pressure, I'll have it more like a liquid, right? So it depends on what you want to do. The whole thing is that at the critical point, you can't differentiate between the liquid and then a vapor state. But then if you want to get it as a liquid or as a vapor, then you would have to adjust your conditions of temperature and pressure so that you get what you are looking for. And we can do that based on the phase diagram. So know that maybe at this pressure and at this temperature, I'll get it as a vapor. At this pressure and at this temperature, I'll get it as a liquid. Are we okay? Okay. Um, I think I wanted to end here. So let me do the next slide. So we are saying that what happens when pressure is applied to water vapor. So what we looked at initially was temperature against volume. Now we want to look at it as the pressure rather against the specific volume. And it's quite similar. The only difference is that the lines move in the opposite direction from the temperature, right? But then it's a very similar concept. So this is what I mean by that. Realize that when we're looking at it as temperature against volume, the lines went this way, and then went that way. But when we're looking at it from the pressure point, the lines are going this way, come this way, and then come down, right? So would talk about what they all mean, and then we'll take it from there. So this is going to be the last thing we'll take today, then I'll take questions, okay? So for the pressure, it's going to work in the other way. So I can have a liquid. I'm keeping the temperature constant this time. So I can have a liquid. If the temperature is being kept constant, oh, this is the last slide. If the temperature is being kept constant, for me to make it a vapor, I have to reduce the pressure. So it gets to a point where, or as I reduce the pressure, the volume will increase because you know that when the pressure is high, the volume is smaller. So as I reduce the pressure, the volume would increase. So you realize here that the pressure is being dropped, is being reduced. And as I'm reducing it, the specific volume will be increasing slightly. Then it gets to the saturation point, so a certain temperature and pressure, where now it can start changing into a vapor. When it becomes fully vapor, a further drop in the pressure is going to cause the volume to increase even more. So this is very similar to the temperature volume curve. But then the only difference is that for temperature, we're increasing the temperature to get the volume to increase and to move to vapor. For pressure, we are reducing the pressure to get the volume to increase and to turn into a vapor. Is that okay? Okay, so this is where we'll end for today, and then tomorrow we'll continue from here. But are there any questions before we go on? Any questions? Any questions, please? I'll be sending the attendance link very soon. So okay, there's a question. Please, what's the question? Okay. Okay, sure. So that's the attendance link. Let's do all to fill it. Right, and then I think we can call it a day. So are there any other questions at all? Okay, then I think we can stop here.